Semiconductor equipment manufacturing, focus on deposition technologies. Welcome to part 2 of our presentation on semiconductor equipment manufacturing, with a focused lens on deposition technologies. Deposition is a critical step in semiconductor fabrication, where materials are carefully layered onto a wafer to build the complex structures that define microchips. This overview will guide you through the essential equipment used in this process, the technologies that enable high-precision layering, and the roles of different tools in achieving uniformity, accuracy, and scalability. From traditional batch reactors to cutting-edge atomic layer deposition systems, we will explore the innovations driving performance in deposition. Our goal is to provide a comprehensive understanding of how deposition fits within the broader manufacturing ecosystem. Whether you're an operator, technician, engineer, or manager, this session will help you connect process fundamentals with the technology platforms used on the fab floor. Let's begin our deep dive into deposition systems and their vital role in semiconductor manufacturing. Other important deposition techniques. In addition to ALD, several other deposition methods play critical roles in semiconductor manufacturing. Physical vapor deposition, or PVD, transfers material to the substrate through physical processes without chemical reactions. The core methods include sputtering, where ion bombardment ejects material from a target, and evaporation, where thermal energy vaporizes the material. Pulsed laser deposition also exists, using laser ablation to deposit films. PVD is widely used for forming metal interconnect layers, diffusion barriers like titanium and titanium nitride, and metal gates or electrodes. Epitaxy focuses on ordered crystalline growth on a substrate with a well-defined orientation relationship. Methods include vapor phase epitaxy, molecular beam epitaxy, and liquid phase epitaxy. Epitaxy is essential for fabricating active device regions, strained silicon layers, and 3-phi compound semiconductors. Electrochemical deposition uses electric current to reduce metal ions onto a conductive surface. It supports methods like electroplating, electroless plating, and pulsed electrodeposition. Key applications include copper interconnects, solder bumps, and through-silicon vias. Comparison of deposition techniques. Different deposition techniques offer distinct trade-offs depending on application needs. PVD provides a high deposition rate but suffers from poor conformality. It delivers good film quality, works well with metals and alloys, and has moderate cost. Epitaxy offers excellent film quality, but its deposition rate is low to medium. It's ideal for semiconductors and has a higher cost due to process complexity. Electrochemical methods, like electroplating, offer high deposition rates and good conformality at a low cost, but are limited to select metals and yield only moderate film quality. CVD and PECVD provide medium deposition rates with good conformality and very good film quality. They support a wide range of materials at a moderate to high cost. ALD stands out for its excellent conformality and film quality, along with a wide material range. However, it has a very low deposition rate and high cost. Emerging techniques aim to increase precision and selectivity. Atomic layer etching is ALD's counterpart for material removal. Selective deposition enables area-specific growth without lithography. Area-selective ALD supports self-aligned patterning essential for advanced nodes. The overall trend is toward increasingly precise, selective, and application-specific deposition. Comparison of deposition techniques. Deposition techniques differ significantly across key performance metrics. This radar chart highlights trade-offs among 5 major methods: CVD, PECVD, ALD, PVD, and epitaxy. Starting with conformality, ALD leads with the best step coverage, followed by CVD and PECVD. PVD performs poorly in this category due to its line-of-sight nature, while epitaxy doesn't prioritize conformality as it focuses on crystalline alignment. For thickness control, ALD once again excels due to atomic scale precision. PECVD and CVD offer moderate control, while PVD and epitaxy are less precise. In terms of deposition rate, PVD and PECVD achieve high throughput, CVD is moderate, and ALD is the slowest due to its sequential nature. Temperature control is strongest in ALD and PECVD, which are suitable for temperature-sensitive applications. Film quality is highest for epitaxy and ALD, with CVD close behind. Lastly, cost efficiency favors PVD and electrochemical methods, whereas ALD and epitaxy tend to be more expensive. Each technique offers distinct strengths, and process selection depends on the specific demands of performance, precision, and cost. Comparison of deposition techniques. Deposition methods differ in operating conditions and suitability for specific applications. CVD operates between 300 and 900 degrees C, offering deposition rates from 10 to 100 nanometers per minute. It delivers good conformality and is ideal for high-quality dielectric films like gate oxides and polysilicon. PECVD operates at lower temperatures, around 200 to 400 degrees C, with faster deposition rates of 20 to 200 nm, making it suitable for low-temperature dielectric and passivation layers, such as SANCs and low-K materials. ALD operates in the 100 to 350 degrees C range and provides extremely precise thickness control, with deposition rates between 0.1 to 0.3 nanometers per cycle. Its conformality is excellent, making it best for high-K gate dielectrics, conformal barriers, and DRAM capacitors. PVD spans from 20 to 500 degrees C with very high deposition rates of 30 to 500 nm, but suffers from poor conformality. It's often used for metal interconnects and gates. Epitaxy requires high temperatures, 500 to 1200 degrees Celsius, and slower rates of 1 to 10 nm. It's the go-to method for growing high-quality crystalline semiconductor layers used in transistor channels, strained silicon, and the 3V compound semiconductors. Market share by manufacturer. The global semiconductor deposition equipment market was valued at $18 billion in 2023, with a robust projected growth rate of 8.6% CAGR through 2032. Applied Materials leads the market with a commanding 26.5% share. Headquartered in Santa Clara, California, they specialize in CVD, PECVD, ALD, and PVD technologies. Notable systems include the Producer R CVD platform and Endura R PVD systems. Lam Research, based in Fremont, California, holds the second position with 19.8% market share, offering products like Vector R PECVD and Striker R ALD systems. ASM International, headquartered in Almere, Netherlands, comes third with 12.4%, specializing in ALD, CVD, and epitaxy. Tokyo Electron from Japan follows with 11.3% share, known for systems like Trias R, SPA, and NT333TM, PECVD. Other players include Oxford Instruments, AI Extron, Ulvac, Vico, and several smaller companies categorized as others, collectively forming the rest of the market. Market share by manufacturer. Oxford Instruments, based in Abingdon, UK, holds 5.8% market share and focuses on ALD and PECVD. Their key products include FlexL R, ALD, and Plasma Pro R systems. AI Extron, headquartered in Herzogenrath, Germany, specializes in epitaxy and MOCVD, with 4.2% market share. Their notable tools include the AIX G5 Plus and AIX R6 Planetary Reactor ER. Ulvac, from Kanagawa, Japan, focuses on PVD and CVD processes. Their SME 200 and Entron TM EX series help them secure 3.7% of the market. Vico, in Plainview, New York, emphasizes MBE and ALD technologies, offering the Propel R, Power GaN MOCVD, and GN Explore R MBE systems, accounting for 2.9%. Other manufacturers like CVD Equipment Corp., PicoSun, Samco, Benek, and Kurt J. Lesker collectively hold a 13.4% share. Overall, the top four manufacturers dominate about 70% of the market. Regionally, the US leads with 55%, followed by Asia at 35% and Europe at 10%. Industry trends include rising integration of multi-process tools and mandatory ALD capabilities for advanced nodes. Industry trends and market outlook. The semiconductor deposition equipment market is expected to grow from $18 billion in 2023 to over $30.13 billion by 2032. This reflects an impressive compound annual growth rate, CAGR, of 8.6% from 2024 to 2032. Notably, the ALD segment is projected to grow even faster, at a rate of 10.2%. Four major industry trends are shaping this growth. First, atomic scale precision is becoming essential. This includes movement toward atomic layer control, rapid adoption of ALD technologies, and tighter sub-nanometer film thickness requirements. Second, 3D architecture evolution is driving demand. High aspect ratio features, GAA transistors, and advanced 3D NAND structures require more sophisticated deposition. Third, there's a strong sustainability focus, aiming to cut waste, use energy-efficient tools, and develop greener chemistries. Finally, manufacturing localization is rising, with government incentives, regional hubs, and supply chain resilience initiatives becoming increasingly important. Regional market insights and future outlook. Regionally, the Asia-Pacific market leads with the highest projected growth rate of 10.5%. Countries like Taiwan, South Korea, and China are driving expansion through aggressive semiconductor investment and manufacturing capacity. North America follows with a 9.2% growth rate driven by innovation and government support, particularly through the CHIPS Act, which is boosting domestic investment. Europe shows a steady 6.8% growth rate, supported by the EU CHIPS Act, which stimulates equipment infrastructure and local manufacturing capabilities. Looking ahead to 2025 through 2030, several emerging opportunities are gaining momentum. These include area-selective deposition technologies, low-temperature processes critical for advanced packaging, and equipment tailored for heterogeneous integration. However, key challenges remain. These include increasing process complexity at advanced nodes, limitations in precursor materials, and the high capital investment required to develop and scale deposition technologies for cutting-edge semiconductor production. Challenges in semiconductor equipment manufacturing. Semiconductor equipment manufacturing faces technical, economic, and supply chain challenges. From a technical standpoint, atomic scale precision is crucial, especially for nodes at 3 nanometers and below, requiring sub-nanometer control. Maintaining film uniformity at scale, less than 1% variation across 300 mm wafers, is also demanding. Other issues include achieving conformal deposition in structures with aspect ratios greater than 100.1, integrating new materials, and handling process temperature limits for low-temperature deposition. Economic challenges are also substantial. Equipment costs have soared, with advanced tools now exceeding $20 million each. Market cyclicality causes spending swings of plus 20–30%, while R&D consumes 15 to 20% of revenue. Additionally, manufacturers face time-to-market pressures and the need to reduce overall cost of ownership. On the supply chain side, key components can have 12 to 18-month lead times. There's also a global shortage of over 30,000 skilled engineers, increasing geopolitical trade constraints, limited access to critical precursor materials, and strict environmental compliance standards. Introduction to semiconductor manufacturing. Semiconductors are materials with electrical conductivity between that of conductors and insulators. They're essential for controlling the flow of electrical current in devices. Silicon is the most widely used semiconductor material due to its abundance and ideal electronic properties. Semiconductors are the foundation of all modern electronics, from smartphones and computers to medical equipment and cars. They are vital for enabling computing, telecommunications, and automotive electronics. Their role is expanding with the growth of AI, the Internet of Things, and cloud computing. These technologies rely on advanced semiconductor chips to function. As a result, the global semiconductor market now exceeds $500 billion in value. The manufacturing process includes 4 major stages: wafer manufacturing, front-end processing, circuit formation, and back-end processing. With over 300 processing steps, Today's chips are made on 300mm wafers at technology nodes as small as 5 nanometers. Importance of semiconductor equipment manufacturing. Semiconductor equipment plays a critical role in enabling the creation of advanced chips. As chip designs become more complex, equipment must support higher precision and performance. These tools directly impact how well chips perform, influencing everything from speed and power consumption to functionality. The ability to pack more transistors into a smaller area depends on the precision of the equipment. This precision is essential for producing chips at leading-edge semiconductor nodes, such as those at 5 nanometers or smaller. Manufacturing equipment must operate at atomic scales, often in the range of 2 to 10 nanometers. At these scales, even the slightest variation can affect chip quality. Equipment precision influences 3 key outcomes: the manufacturing yield or percentage of functional chips, the electrical and physical performance of those chips, and the power efficiency of the final products they're used in. Economic impact of semiconductor equipment manufacturing. In 2023, the global market for semiconductor equipment surpassed $110 billion, reflecting its immense scale and strategic importance. The industry is expected to grow at a compound annual growth rate, or KGR, of 7 to 10% through 2030. This steady and substantial growth is fueled by increasing global demand for more powerful and efficient semiconductor chips. Semiconductor equipment is also a cornerstone of national economic competitiveness. Countries that lead in this sector have a strong edge in global technology markets, innovation, and supply chain resilience. The equipment industry directly supports the broader $500+ billion semiconductor market, enabling fabrication of advanced logic, memory, and sensor devices. A key insight is that deposition equipment alone accounts for about 18% of the total equipment market, underscoring its critical role in manufacturing. As chip complexity increases, demand for precision equipment will continue to rise. Challenges in semiconductor equipment manufacturing. Deposition technologies, such as CVD, PECVD, ALD, and PVD, face a range of challenges across multiple dimensions. These include high technical complexity, long time to market, equipment cost, process control, supply chain issues, and material limitations. ALD, in particular, presents some of the most intense challenges due to its atomic-level precision requirements. In response, the industry is deploying multiple strategies. Collaborative R&D consortia bring together universities and national labs for innovation. Vertical integration helps manufacturers secure critical components. AI-enhanced process control, especially through machine learning, enables better optimization of deposition parameters. Workforce development is key, with training programs and university partnerships addressing talent shortages. Government partnerships, like the CHIPS Act, provide essential funding. As the industry moves toward 2 nanometer and smaller nodes, critical deposition-specific challenges include ultra-thin film control, new high-K materials, minimizing interface defects, and enabling area-selective deposition for pattern precision. Future innovations in deposition equipment. Deposition technologies are evolving to meet the stringent demands of future semiconductor nodes. One major advancement is area-selective deposition, which precisely deposits materials only on targeted surface regions, eliminating certain lithography steps. Key innovations include self-assembled monolayer blocking, use of selective inhibitors or catalysts, and surface activation through directed energy. This technology is expected to emerge between 2025 and 2027. Another significant breakthrough is atomic-level engineering, which enables precise layer-by-layer material control with real-time in-situ monitoring and feedback. Important developments in this area include AI-driven process control, multi-wavelength ellipsometry for film characterization, and digital twin modeling for simulation and optimization. These are expected to arrive between 2024 and 2026. Lastly, low-energy plasma ALD is advancing, providing ultra-low temperature deposition with minimal substrate damage. Anticipated improvements include room temperature processing, reduced ion bombardment, and remote plasma generation, with implementation projected from 2025 to 2028. Environmental considerations. Different deposition technologies have varied environmental footprints. Comparing CVD, PECVD, ALD, and PVD reveals key differences in greenhouse gas emissions, energy consumption, chemical usage, and water usage. CVD shows the highest overall impact across all four categories, particularly in GHG emissions and energy consumption. PECVD also demonstrates elevated levels, though slightly lower than CVD. ALD stands out for lower GHG and water usage, but its chemical usage remains relatively high. PVD, while generally lower in impact, still presents notable energy consumption levels. To address these concerns, several companies are leading sustainability efforts. Applied Materials achieved an 80% reduction in PFC emissions through process optimization in 2023. Lam Research implemented low-temperature ALD to cut energy usage by 45% in 2024. ASM International is piloting a precursor recycling system, recovering 65% of materials. Tokyo Electron is developing a system to cut ultra-pure water usage by 70%. Industry-wide, ambitious goals target 50% GHG reduction, 40% water reduction, and 90% waste diversion by 2030. Summary and key takeaways. Deposition technologies form the backbone of semiconductor fabrication, with each method offering distinct advantages. Chemical vapor deposition, or CVD, produces high-quality films between 300 and 900 degrees C and is ideal for dielectrics and gate oxides. Plasma-enhanced CVD operates at lower temperatures using plasma activation, well-suited for passivation and low-K dielectrics. Atomic layer deposition enables atomic-scale precision, making it the top choice for high-K dielectrics and conformal barriers. Physical vapor deposition, which transfers material without chemical reactions, is commonly used for metal interconnects and barriers. Deposition is repeated 15 to 30 times per chip, making it a critical step. Technologies are evolving toward atomic-scale precision and better conformality. Each technique is complementary. There's no one-size-fits-all. The top four manufacturers dominate roughly 70% of the market. With an 8.6% compound growth rate through 2032, the trajectory is strong. Future developments include area-selective deposition, AI-driven control, localized manufacturing, and quantum-engineered materials. Key success factors include innovation, integration, sustainability, and cost reduction. Comparative advantages by technology. Each deposition method brings unique strengths and trade-offs, making it essential to evaluate them by key performance features. In terms of conformality, ALD provides excellent coverage, especially over complex topographies, while CVD and PECVD offer good conformality, and PVD is limited. Thickness control is where ALD excels, achieving atomic-level precision. PECVD and CVD maintain good to moderate control, while PVD falls in the moderate range. When considering deposition rate, PVD and PECVD both stand out with very high rates, making them suitable for high-throughput environments. ALD, by contrast, has a very low deposition rate due to its self-limiting reaction mechanism. CVD offers a high rate, striking a balance. Regarding process temperature, PVD has the widest range, from 20 to 500 degrees C. ALD operates at low to moderate temperatures, typically 100 NAR 350 degrees C, while PECVD and CVD function in the 200 NAR 900 degrees C range. Optimal manufacturing often blends these techniques for best results.